is equal to v squared over r, where r here is the radius of that circle. We could also alternatively express that as 4 pi squared r divided by t squared, where t is the time it takes for whatever we have to travel around the circle once. We could also get an expression for the speed of that object around the circle, which is just 2 pi r over t. And the speed is really just the distance over time. So the time is the big T over here is the period, so the time it takes to go around all the way around the circle once, and this is the circumference of the circle. Right, so however long it takes to travel around once, if it's traveling at a constant speed, if I just take that distance and divide by t, divide by the period, I get the speed at any one instant, as long as it's in uniform circular motion. By the way, this would be going around in this direction.
What is the variable in the center of the switch?
This is the A vector. Okay? So I'm drawing it as a vector here, but this is the same, it's the same as this radial acceleration over here. But here it's just the magnitude. Okay? I'm not giving a direction here because the direction of A is always changing, right? It's always towards the center of the circle, but the magnitude is the same. The magnitude stays constant, but the direction of A is always changing. The magnitude of V is also constant, but its direction is also changing. Right? As I go around the circle, right, it said, if I was up here, my velocity would be in this direction. Right? So V and A are changing in direction, but they're not changing in magnitude. So if I were to ask you, is the velocity in uniform circular motion constant, you would say no. If I were to ask you that, is the speed in uniform circular motion constant, you would say yes. Because the speed is the magnitude, the velocity is a vector. The vector, when the direction changes, is no longer constant.
If that's slowing down, what is that acceleration?
Okay, if it's slowing down, then there's a component of the acceleration that's acting opposite of the velocity, right? And so as a result, I have to add that component to this acceleration that's headed towards the center of the circle, the vector addition, and so the resulting vector would be backwards. Would be sort of diagonally backwards in this direction. Okay? So I'll draw it. So right, if we have V is in this direction, but it's decreasing, so that we have some A, tangential A, that's in this direction. Then we still have A radial, right? It's in this direction, but the sum total of these two vectors would then be in that direction. So this would be your A total between the two of them. Okay. All right. So the other thing I just wanted to stick in here as well is that if you're calculating weight, I hope that everybody remembers this. Weight is a vector, always acts downwards. Is always mg, and then the g gets the little vector symbol because mass is a scalar, right? Mass is never a vector.
Professor,
Yes.
what was that second circle? What does that represent when you, like, what situation does that represent?
So this is not uniform circular motion, by the way, because in uniform circular motion you have to have a constant v. All right. So he asked, what happens if I have some acceleration that is along the tangential direction? Right. And so that's what this is. This type of tangential acceleration is acting back in this direction, so it's slowing down the speed as it goes around the circle, right? So slowing down, and as a result, my acceleration is not directed towards the center of the circle. A component of it acts in this direction, and so therefore the total acceleration is in this diagonal direction, up and to the left. All right, so this is not. That's not uniform circular motion. All right. Newton's laws, which hopefully you already have memorized. The first law is that the sum of the forces on some object, when the sum of the forces is equal to 0, right, there's no acceleration. And so in this situation, I can either have the velocity is equal to 0, or I can have a velocity that is not equal to 0, but the acceleration must equal 0. Right? So that's saying basically that I put some object in motion, and if the sum of the forces on that object is 0, it will continue in motion with no acceleration forever. Okay? We don't usually have that situation. Usually there's something that's slowing things down. Usually there's friction, usually there's air resistance, some other thing. Your little brother pushing against you, preventing you from getting some cookies. You know, there's some force preventing you from continuing in motion along some path. Right? So that's Newton's first law. The second law is that the sum of the forces, when there is a sum of the forces that is non-zero, is equal to the mass times the acceleration. The acceleration again is a vector here. So here the acceleration is not equal to 0, but we can have v is equal to 0 or v not equal to 0. So most of the time we think of this as v not being equal to 0, but there are situations where your velocity is 0, but your acceleration is not 0. I'll give you an example. You throw a ball straight up in the air. The ball reaches the top of its flight. It's momentarily at rest at the very top of its flight, right? And then it starts to fall. Okay? But at all times during that flight, its velocity is changing, right? Its velocity starts with some initial velocity upwards, right? And it reaches some top point at v is equal to 0, and then it starts to fall and it comes back down. And it's, if you ignore air resistance, it comes back down. And it reaches your hand at the same velocity that it left your hand. But at that very top point is v is equal to 0. At all points, though, within that flight, there are no external forces acting. Again, we're ignoring air resistance, so there's no external forces acting on that ball besides gravity. So that's the only force acting on it. And so the acceleration at all points along that flight is downwards. So even at the top of your flight, you have some acceleration downwards, right? But your v is equal to 0 at that instant. Okay, so you can have situations where the acceleration is 0. The acceleration is non-zero, but your velocity is 0. And then the third law is that if I have some force A on B, some force on some object due to another object, exerting the force, that's equal to minus the force of B on A. And so the example that we had for that was a person kicking a soccer ball. This is my poorly drawn soccer ball. And the point that we made was that the person kicks the soccer ball exerts the same amount of force on the person's leg as the leg exerts on the ball, right? And then the difference in their acceleration, right, is just due to the fact that the ball is much less massive than the person's leg, right? So the acceleration of the leg is opposite the direction of the kick, right? It gets accelerated backwards when the person kicks the ball, and the ball accelerates off in this direction. But the magnitude of those forces is the same. It's equal and opposite. Another way of stating this sometimes that people use is that for every action, there's an equal and opposite reaction, right? So that's another way of stating Newton's third law. And then I also want to point out for Newton's second law is that if we break this down into components, so the sum of the forces in the x direction is equal to the mass times the acceleration in the x direction. Same thing with the y direction. Same thing with the z direction. All right. So I mentioned friction, and just to remind ourselves how friction is defined. Friction is a contact force, so there has to be some contact between the surface or maybe some air and some object in order for there to be some friction. Usually we think of it as friction between a surface and some object. And there's two types of friction, right? There's static friction, which is less than or equal some maximum static friction, which is equal to the coefficient of static friction, us, times n, or the normal force. So everybody remember what the normal force is? The normal force is the contact force that's acting back up on you due to some surface. So right now, I'm standing on the stage, there's two forces acting. There's my weight down, and there's a normal force upwards, right? The normal force is exactly balancing my weight down because, as far as I can tell, I'm not accelerating in the y direction, right? I'm not accelerating up or down. So, that normal force is balancing my weight downwards. And so, if someone were to try to come up here and try to push me across the stage, they would have a hard time doing that because my rubber shoes have a pretty high coefficient of static friction with the stage. It would be difficult to push me, the rubber soles on my shoes would make it difficult for them to push me across the stage. However, if you put me on some block of ice, then they have an easier job of pushing me across the stage because the coefficient of static friction will be lower, right, in order to get me going, right? So that's if I'm stopped, right? And so I can exert a larger force up to a point where I exert a large enough force, the maximum static friction force allowed, at which point I start sliding, right? And once I start sliding, then I'm undergoing some kinetic friction, which is just given by coefficient of kinetic friction, UK, times, again, the normal force, right? And the kinetic friction coefficient is usually a little bit lower than the static friction coefficient. So you go up to some maximum in terms of your static friction force, and then as soon as you start sliding, the force that you have to exert to keep somebody moving at a constant speed due to the to oppose that kinetic friction is a little bit less than the maximum for static friction. I think I'm not going to reproduce that graph, but I think you hopefully remember that. All right. So one of the things that's important when setting up problems like this for Newton's laws is making sure that you draw free-body diagrams. And as an example, something that you've seen before, a block on an inclined plane. All right, so if we have some plane that's inclined at some angle, let's call that theta, right? We have this block, and let's say this block is at rest, so it has zero velocity. And let's say I want to draw a free body diagram for this block. Well, I have to draw, I represent the block with a little dot, and then to draw a free body diagram, I try to represent all the forces with vectors. So the easiest one that's always there for problems on Earth is the weight downwards, right? Then I know that because it's sitting on this surface, there's a contact force with that surface, and I have a normal force in this direction. I'm not drawing this to scale, although I should try harder to draw this to scale. And then, in addition to that, because it has v is equal to 0, there must be some force opposing the force of the weight that would tend to bring it down this plane, and so I know that that must be some static friction force acting up the plane that's preventing it from sliding downwards. So in your free body diagram, you want to represent all the forces, and then do what I did not do. Try to draw each vector to some scale that's representative. All right, so in other words, that's the length of each vector. And so also as a reminder, V and A, for instance, so our velocity and our acceleration do not belong on a free body diagram. Excuse me. Right, so they have to be drawn separately. So if I were to draw some velocity vector for this, right, I would draw it somewhere that is not attached to my little point. Right, I would draw it off to the side. Okay. So let's talk about work for a second. So there's a couple different situations where we have work. Excuse me. In the case where I have a constant force, work, which has units of joules, by the way, is force